-230 degrees Celsius. That's the temperature inside the permanently shadowed craters at the Moon's south pole, where NASA plans to build humanity's first permanent home beyond Earth by the early 2040s. These ancient shadows, untouched by sunlight for billions of years, sit within tens of kilometers of peaks that receive near-continuous sunlight, creating an alien scene of eternal light and eternal darkness that will either make or break the most ambitious construction project in human history. This isn't just another mission to plant flags and collect rocks. The Artemis program represents a fundamental shift from the sprint mentality of Apollo to building a self-sustaining base 240,000 miles from Earth, where crews will rotate through 6-month assignments like astronauts aboard the International Space Station. The timeline is aggressive, the technology is largely unproven at lunar scale, and the margin for error approaches zero when every supply delivery costs millions of dollars and takes 3 days to arrive. The question isn't whether individual technologies work in laboratory conditions. Solar panels generate electricity, nuclear reactors produce power, and three-dimensional printers can shape structures from raw materials. The real mystery lies in integration, in making these systems work together reliably in an environment that combines the radiation exposure of deep space with the abrasive dust of an industrial sandblasting operation and temperature swings that would shatter most materials designed for Earth. Building a permanent lunar base means solving problems that don't exist anywhere else in the solar system. Every kilogram of water must either be shipped from Earth at enormous cost or extracted from ice deposits that may or may not exist in the quantities NASA's models predict. Every structure must withstand cosmic radiation that delivers 12,000 to 20,000 millirem annually without shielding, compared to the 300 to 400 millirem that airline crews experience in Earth's protective magnetosphere. And every piece of equipment must function flawlessly despite lunar dust that carries an electrostatic charge and features edges sharp enough to cut through spacesuit materials. The race against radiation and dust begins the moment astronauts step onto the lunar surface. Galactic cosmic rays, high-energy particles traveling at nearly the speed of light, bombard the Moon without the protection of Earth's magnetic field or atmosphere. These invisible bullets deliver a constant dose of radiation that limits how long crews can remain on the surface before exceeding NASA's safety thresholds for increased cancer risk. But cosmic rays represent only the baseline threat. Solar particle events, massive eruptions from the sun's surface, can deliver radiation doses that cause acute sickness within hours. The August 1972 solar storm would have delivered 200 rem to an unshielded astronaut, enough to cause nausea, fatigue, and potential long-term health effects. NASA's solution involves building storm shelters with thick regolith shielding, but crews would have only 10 to 20 minutes warning to reach safety once space weather satellites detect an incoming particle stream. Lunar dust presents a more insidious challenge than radiation because it affects every system, every seal, and every moving part on the base. This isn't ordinary dirt. Billions of years of micrometeorite impacts have ground lunar rock into particles with razor-sharp edges that never weathered smooth because the Moon lacks wind and water. The vacuum environment preserves these microscopic glass shards in their most abrasive form, while solar radiation gives each particle an electrostatic charge that makes dust cling to surfaces despite the absence of air or moisture. Apollo astronauts discovered that lunar dust infiltrated everything. The abrasive particles scratched helmet visors, clogged air filters, and even penetrated the seals on sample containers that were supposed to preserve lunar material in vacuum. For short missions lasting a few days, dust represented an annoyance. For permanent bases operating continuously, dust infiltration could disable life support systems, degrade solar panel efficiency, and wear out mechanical components years ahead of schedule. NASA's proposed solution involves electrodynamic dust shields that use electrical fields to repel charged particles before they can settle on critical surfaces. The technology works in laboratory demonstrations, consuming modest amounts of power to create invisible barriers around solar panels, habitat windows, and equipment housings. But the lunar environment presents variables that Earth-based testing cannot fully replicate, including the complex chemistry of space weathering and the long-term behavior of electrical systems exposed to cosmic radiation. Mining water in the permanently shadowed regions represents the make-or-break technology for lunar-based sustainability. Without successful extraction of water ice from lunar soil, every drop of drinking water, every breath of oxygen, and every kilogram of rocket fuel must be transported from Earth at costs that make permanent habitation economically impossible. The water exists, according to orbital surveys that detect hydrogen signatures consistent with ice deposits. Estimates suggest 100 to 300 million metric tons of water ice accumulated in the south polar regions over billions of years, trapped in cold storage at temperatures that would freeze carbon dioxide solid. But estimates and reality often diverge when drilling equipment meets actual lunar conditions. The Viper rover mission was canceled by NASA in July 2024 due to cost overruns and schedule delays, though NASA continues to seek alternative approaches to map lunar ice deposits. This represents more than a scientific setback because Viper's data would directly inform the placement and design of permanent extraction facilities. Building water processing plants without detailed knowledge of ice distribution, depth, and concentration resembles constructing oil refineries without geological surveys. The extraction process itself demands heating regolith to temperatures that sublime water ice directly into vapor, then condensing that vapor into liquid water through cooling systems. Energy requirements range from 2 to 4 kilowatt-hours per kilogram of extracted water, assuming regolith contains 10 to 15% water ice by mass. For a base supporting 4 to 6 crew members, daily water needs for drinking, hygiene, and life support approach 20 to 30 kilograms, requiring large and continuous energy input for processing operations. Water serves multiple functions beyond basic human consumption. Electrolysis splits water molecules into hydrogen and oxygen, providing breathable air and rocket propellant for return vehicles. Hydrogen and oxygen can power fuel cells that generate electricity and produce water as a byproduct, creating closed-loop systems that maximize resource efficiency. Water also functions as radiation shielding because hydrogen atoms effectively absorb cosmic ray energy, making water tanks serve double duty as both storage and protection. The technology readiness level for integrated water extraction systems remains at 3 to 4 on NASA's 9-point scale, indicating proof of concept or laboratory demonstration rather than the 8 to 9 rating required for spaceflight hardware. Individual components work in controlled conditions, but the complete system from drilling through purification to storage has never operated under authentic lunar conditions for extended periods. Building a city with moonbeams and atoms requires power generation systems that function reliably despite extreme temperature variations and the moon's 14-day night cycle. Solar panels at the lunar South Pole receive minimal energy because the sun never rises more than 3 to 5 degrees above the horizon, creating illumination conditions similar to perpetual winter twilight. Even on peaks of eternal light, solar panel efficiency drops significantly compared to orbital installations that receive direct sunlight. NASA's kilopower nuclear reactor offers an alternative that operates independently of solar conditions. The 10-kilowatt system weighs 4 to 6 metric tons and converts heat from uranium fission directly into electricity through Stirling engines, eliminating the steam turbines and cooling systems that make terrestrial nuclear plants massive and complex. The reactor would be positioned 100 to 200 meters from crew habitats to minimize radiation exposure while providing steady power for life support, heating, and industrial operations. Construction methodologies combine techniques borrowed from terrestrial three-dimensional printing with materials science adapted for vacuum conditions. Printing structures from lunar regolith requires mixing local soil with binder materials to create concrete-like substances with compressive strengths reaching 10 to 30 megapascals, comparable to building materials used in earth construction. The process involves excavating regolith, processing it to optimize particle size distribution, then depositing layers with binder applied between each level to build walls, foundations, and radiation shields. Alternative construction approaches use concentrated solar energy or directed heating to sinter regolith particles into fused masses without requiring binder material shipped from Earth. Sintering creates durable structures but demands precise temperature control to avoid creating brittle materials that crack under thermal stress. Both printing and sintering would initially rely on teleoperation or autonomous systems because real-time human supervision would be inefficient given communication delays and the continuous energy requirements for construction operations. The Lunar Terrain Vehicle represents the crew's lifeline for operations beyond walking distance from the base camp. This pressurized rover, exceeding 6 meters in length, provides 4 astronauts with shirt-sleeve mobility for traverses up to 20 to 30 kilometers from base on single sorties. The vehicle uses regenerative fuel cells powered by hydrogen and oxygen derived from lunar water extraction, creating a closed-loop transportation system that produces water as a byproduct of generating electricity for propulsion. The 20-year countdown from current capabilities to permanent lunar presence follows a carefully orchestrated sequence of missions, each building on the previous accomplishment while adding new capabilities. Artemis 1 completed its uncrewed test flight in November 2022, validating the Space Launch System rocket and Orion spacecraft for deep space operations. Artemis 2, planned for September 2025, will carry 4 astronauts on a lunar flyby mission to test crew procedures and emergency protocols before surface operations begin. Artemis 3, targeting September 2026 for the first crewed landing, will deploy initial base camp infrastructure during approximately 1 week of surface operations. Subsequent missions spaced 1 to 2 years apart will deliver additional habitat modules, power systems, and resource extraction equipment until the base achieves self-sufficiency for basic life support and fuel production. The transition to permanent presence with crews rotating through 6-month assignments is planned for the early 2040s. The financial reality involves development costs approaching $100 to $150 billion through the first surface landing, with recurring operational expenses ranging from $5 to $20 billion annually for sustained base operations. These figures assume successful technology development, sustained congressional funding across multiple election cycles, and absence of major setbacks that could delay the program by years. International partnerships distribute both costs and technical responsibilities across multiple space agencies and commercial contractors. The European Space Agency provides Orion service modules that handle propulsion and power generation for deep space missions. Japan contributes habitat components and scientific instruments. Commercial companies including SpaceX, Blue Origin, and Axiom Space develop cargo delivery systems, landing vehicles, and habitat modules that complement NASA's core capabilities. The Artemis Accords, signed by more than 40 nations as of 2024, establish legal frameworks for resource extraction rights and operational safety zones around lunar installations. This international cooperation creates redundancy that helps ensure program continuation even if individual contractors encounter delays or technical problems. Critical unknowns remain that could significantly impact the timeline and feasibility of permanent lunar habitation. The actual quantity, distribution, and accessibility of water ice deposits awaits ground truth verification through robotic missions. The long-term effectiveness of dust mitigation technologies requires testing under authentic lunar conditions over months or years of continuous operation. The reliability and maintenance requirements for life support systems operating in the abrasive lunar environment remain poorly quantified because no comparable systems have operated for extended periods beyond Earth's protective environment. The economic sustainability of permanent lunar presence depends on reducing transportation costs through next-generation heavy-lift vehicles and successful implementation of in-situ resource utilization that eliminates the need to ship basic consumables from Earth. Current projections suggest these goals are achievable, but the detailed economics of lunar supply chains await demonstration at operational scale. NASA's plan for a permanent moon base is technically possible based on current understanding of physics and engineering principles, with primary constraints residing in technology integration, sustained funding, and resolution of operational unknowns that can only be answered through actual lunar experience. The individual technologies exist in various stages of development, from laboratory demonstrations to near-flight-ready systems. The integration challenge, while large, does not appear to involve fundamentally intractable problems absent from terrestrial spaceflight experience. The early 2040 timeline for permanent presence represents an aggressive but achievable projection, contingent on successful execution of near-term Artemis missions and continued international cooperation. Any major technical failure, funding disruption, or safety incident could extend the timeline by years, but the convergence of government space agencies, commercial companies, and international partners around this common vision suggests the technical and programmatic challenges may be addressable through sustained commitment and cooperation. The answer returns us to those permanently shadowed craters where temperatures remain at -230 degrees Celsius, just kilometers from peaks where sunlight never sets. NASA's plan transforms this scene of extremes from humanity's greatest environmental challenge into our first permanent foothold beyond Earth. The physics permits success, the technologies show promise, but the ultimate test lies not in laboratory conditions or computer simulations, but in the harsh reality of making these systems work together reliably in the most unforgiving environment humans have ever attempted to call home.